Yes, now I started. Okay, so maybe at the moment we don't know the answer. So let's see, we start the lecture and we will find the answers throughout the lecture. Okay. So yeah, this is the outline of today's talk. We'll be talking a lot about graphs and trees. Okay. Just as you are few, and I suppose that you are here to in order to get something from the lecture. So do not hesitate and ask questions once something won't be clear. Again, this is a introductory lecture, so maybe some of you already had some programming algorithmics course, and indeed the problems of graphs and building a search tree is a kind of cornerstone of algorithms. So maybe some of you heard some of the terms we'll be discussing. Okay, so this is the usual, one of the usual problems that people come out when someone asks about what is the search and what is the purpose of the algorithm. This is a shot of a map. This is the map from the book, one of the recommended book we are using, the AI modern approach. And give me a sec, I will, okay. So, and this is our start. And here, this is our goal. So we want to get in here, okay? And the map we have. And say the numbers correspond to the kilometers, to the distance between the cities. Okay. So this is the situation where we know everything about situation. Okay. Think about that we have a car, okay, and we want to go from S to G. So what's the state in here? If you could say or type into the comment, into the chat. Yes, each state is unique. So think about that you are somewhere in the middle of the problem. So you are, say, with your car, you are at this particular city, okay? So what would be the state? That would completely describe the problem, the situation, the current situation. Yes, that's the city. So it's kind of the position of the car, say, okay? So the state is... and think about that you are the driver. You know that you are here, for instance, in S, and you want to go to here, to G. So what is the sought solution? Could you think about and type in a few words or say? Okay, no one's typing.
Excuse me, what was the question?
So the question was, think that you are in a car in the state S, so in the city Arad, and you want to go to Bucharest, okay, to Chi. And you have a computer program that gives you a solution. My question is, what's the solution you are looking for?
The one with the shortest solution.
Okay, in general, okay, there could be the optimality. We still didn't discuss the optimality, but indeed the sought solution is the sequence of the cities, say. Okay, so imagine that a possible path is like this. Of course, I'm not sure if it's optimal or not, but the sought solution is, say, Arad, Sibiu, Rimini, and so on. So the sequence of the city. So say a path plan. Okay, so not only what I'm trying to emphasize that, of course, getting into G is the ultimate goal. This is where we want to be at the end. But the sought solution is the sequence of cities, so sequence of paths or sequence of actions in all the states. Okay. Because the tasks here could be different, right? So the task here is to go to S to G, but the task could be also visit all cities at least once. This is the known traveling salesman problem. Okay, so there could be many more tasks. So we already agreed that the states, a state means position in the city. The actions I'm doing is driving in cities, and the sought solution is the path, the sequence of the cities in here. And of course, the question is, what would be the design of a computer program that delivers a good solution? We don't know what the good means, but we will go into it in a minute. Of course, we want design a general methodology for any state space search problem. So could you remind me here, what would be the states, what would be a state here in a puzzle problem? So this is the n-1 puzzle we discussed last week. So what would be the states?
The sequence of numbers.
Yes, indeed. So we can enforce some ordering like that. To make it more simple for a computer. And this, to describe this state, we can write 7, 2, 4, 5, a special symbol for nothing. Okay, say the space. Okay, so we know how to design a state. So what will be the action?
Moving up or down or left or right.
Yes, so we do have several possible movements. In this particular case, we have 4 possible movements. So it can be also seen as a kind of swap. for instance, okay, no, that would be too confusing. So in fact, it can be also seen in the opposite, that we can see the movement as a movement of the, not like that, as I put the blue arrows, but as the movement of the blank space. Okay, so here I can say, okay, I can move blank here and so on. But it's just methodology, and then it depends how you implement. Okay, so that's the action solution we already know. So that's the again sequence of states that leads to a goal solution, right? And of course, probably we want to do it somewhat reasonably, which we can say that we want to find a solution that is cheapest, okay, for instance. So what will be the cost here? Any suggestion?
Maybe the time taken.
Yeah, definitely. And here probably the better would be the number of movements, right? So because of course, I mean, it corresponds to the time. If we say that one action takes a constant time, then this is the same. But here, more natural would be to measure the number of steps I need to perform to achieve the final goal state. Okay, here this is again a classical toy problem for robotics. We have two rooms. Okay, this is the small flat, this is two rooms. I have some garbage or dust in either left or right room. And I have a cleaning robot. And of course, the goal is to clean the whole flat. So I can do what I can do actually. What would be the actions?
I can move left or right or take the garbage.
Exactly. So I have three actions. And left, right, and maybe suck, if it's the vacuum cleaner, suck the garbage. Okay, it can be pick up or something, it depends. Exactly. So okay, sorry, that was the actions. The states, what would be the states?
Position of the vacuum.
Yes, and
And if the how much garbage is still left.
yes, indeed. So these were the actions, and it's the state. So that's the robot plus dirt position. And again, as usual, the solution is a sequence of actions. Looking for a sequence of action that yields a goal, which is here the completely clean room. Okay, and again, the cost is quite natural. The number of movement of the robot, so I can optimize for the robot energy, for instance. Okay, interesting question could be, okay, we have a robot position and dirt position. So how many possible states do we have here? Could you try any guesses? So someone says 8. What the others? Okay, so indeed, we have two possible choices for the agent location. And for every location, there could be a dirt versus no dirt. So it's indeed the 8 possible possible states. So the most difficult problem is to formalize it in a search problem language. Okay, because once you do it, and you have a engine that does a search in a state space, then you are done. Simply your engine can solve it. Okay, so for a definition of the search problem, we need the state space. I mean, the definition, what start, initial, what's the current state, and so on. We have to be sure what are the possible actions. Then something we until now didn't talk much about, but we will come to in a later, and it's good to understand it from here. So given a state, I perform an action, okay, and this returns some state. Okay, so one can say that let's say that I want to get some different state by some transition. If I'm in state S, and if I perform the action A. Interestingly for you, this is typically what in real, I mean, if you are dealing with a robot, this is something you do not design this, right? Because this is the property of the environment. Okay, so your task typically is for given S, from given state, your algorithm is supposed to take a proper action. Okay, and the transition model is part of the environment. So unless you are creator of a simulator, for instance, this is something you typically don't program. This is something you don't code. Okay, and of course you need the goal test. And again, this is for most of the problems we will be discussing throughout this lecture. This will be given for you. Like, I mean, the environment, you can say, okay, am I in the city? Or are all rooms clean? So this is again the property of the environment. Okay, so I suppose that most of you had some course about graphs, so about graph theory. Okay, so whenever we will be talking about graphs, we will be talking about this kind of graphs. So a set of nodes and arcs or branches or simply connecting lines between the node edges. Sorry, I was looking for the good word. So maybe arcs. Someone says better edges. So again, not like those graphs, you know. And what is important here to remember again, that we need that each state is unique, occurs only once in the state space. Okay. So again, this is a kind of abstraction that describes our search problem, our problem. So in the map, it's quite natural. The nodes are the cities and the edges are the existing paths in between, right? In the n-1 puzzle, it's a bit more difficult. The states, as we remember, are the 9 or n vectors describing the positions of the stones. And obviously, we can't go from all the states to the other. So again, there are some edges between some states. And the fact is that, for instance, here we do have the map, right? So we do have the graph in advance, say. But for instance, in the n-1 puzzle, we don't have this graph. And it will be immensely time consuming to build the whole graph first and then solve the problem. Okay, we know that there is indeed some graphs underlying the problem, but we don't need really to build it in advance. It's important to I mean, this is my suggestion how to create a mental model of the problem. I mean, you can create yours, but this would be mine. So this is kind of abstraction of the problem. And what is more important, that the behavior of our algorithm, of our solution, say, could be described by something which is called search trees. Okay, so we do have a So we already know that our problems can be described by a graph language in the form of graphs, and our algorithm, as we will see, can be described by language from search trees. So what's the main difference between tree and graph? Can someone type it?
Tree has no circles.
Yeah, indeed, no cycles. So, and why tree? Okay, let's think it about like that. So we are at a particular city, and then we can go to several cities, which have a direct connection with the starting, and from the next cities we can go to some other cities, and so on until we end up somewhere here in the in the goal state. So in a tree, we have a slightly different methodology, vocabulary, say. Those elements are called nodes. And each node has a ancestor except the starting one, and also some successors, of course, until the very end of the trees. Essentially, the nodes also contains the state information. So here, say that those characters represent the cities. Okay, but question is, can it happen, for instance, that a particular city will be, so particular state will be twice or even more in the search tree? So just a quick survey. Sorry, Once again. No.
Can you please repeat the question?
So my question is, can it happen? Okay, first, we remember that states must be unique. So in a graphs, each city appeared only once. My question is, can it happen that a state is a member of several nodes? So say the city A, can it happen that it appears twice or even more time in a search tree during the execution of the algorithm? Okay, I'll publish. So it's equal. It says it's in check. Give me a sec. I will change the. Wait.
It's in the language of the people's browser, so it's in check only for you.
Yes,
results.
but now when I publish it into the PDF, you also see the check, right? The ANO and
No.
net. No, you see English.
I see French, but others will see in their language.
Okay, so it's fine. So it does the translation for you, so it's good. Perfect. Okay, very well done. Okay, so we'll see. So someone says yes, someone says no. I think that actually understanding the difference between between space graph and the search tree is probably the most important. Once you, fully comprehend it, fully grasp it, then the rest is relatively easy, right? Okay, so think about that we are now at the state S, right? So that corresponds to here. Now from S, we see that we can go to A, we can go to B, and we can go to C. Okay. Think about that. The environment gives you the answers like for a given states, say some function get next states for the S, and this will give you the answers A, B, C, and even for instance with the path cost we'll come to it later. Okay, so we are S, and we are saying, okay, what are the next states? Either that's information encoded in the map or in some grammar that describes the, for instance, the n- puzzle. So the system tells us what are the next possible steps. Okay, A, B, C. And of course, so we have the successors of the start of the start node. Okay. And now, of course, we have somehow to select how we will continue. So say now we are in A, so we selected A. And we can see, okay, from A, we can go to S. So the next states function returns answers S, and that will be probably it, as I see it here. Okay. So, okay, I am building a tree once again. So that tree somehow encodes the behavior of my algorithm. So we see that we created a new node that contains the S, the description of the state. This node says current state of the problem, current position of the car is in the city S, which was the array. Okay. But of course, this node is different than this one, right? So those two nodes contain both S, like encoding where the car is, but these nodes already contains the information that I went to that particular node from here, or at least it has to. It depends how you implement it. But for instance, we will see that it's quite needed that your nodes remember also the ancestors. So all these nodes remember the ancestors, so I can recover the path I got here. So I can, if you need it, I can come up back to the initial node. And then here I can continue here. So this essentially then repeats to the A, B, C, and so on. So, okay, I use a different strategy. I'm exploring the node B. And I continue. Up. Sorry, I was too fast. So for instance, here I can see we still didn't talk how to top the search. We see here that we have the G, the goal state, for instance, here twice. And we intuitively feel the stopping criteria should be in a way that, for instance, we will have to make sure that, for instance, if we had stopped here, we should be quite sure that this part is the best one and not this one. Okay, so we see that we need some strategy. Okay, so what is interesting to see here that the search tree can be indeed much bigger than the space graph. Okay. The space graph can have a few edges, but the search graph can be much bigger, and of course, even worse, if done unwisely, it can be infinite. Okay, we'll come to that in a minute. So in order to understand how to create a program, it's good to use some methodology or vocabulary. So this is the state now, and we want to explore the possibility where we can move from this deputy. This Arad city became gray, saying that we explore this particular state. And those states are coming to explore. Okay, so nodes at the frontier or at the border is known and was not known. Okay, here this previously was explored, so now it to get of explored nodes, and frontier state now here. And those states are still unknown. So we can see that the tree is built incrementally, and we are somehow revealing more and more from the original state space. Sorry. So what we will need for our algorithm, okay? So now we explored this Arad and we had the 3 frontiers. Then we expand Sibiu city, this one, and now we have the frontier, the border of what is known and what is not known. And now, of course, the question is, what node to explode next? So should I take this and explore here, or should I take here, explore here, or here, and so on? So we will see at the end that, okay, someone's going to check. Some problem is voice, okay. Okay. It's clear now, okay. Okay, hopefully it's now better. I know I'm unfortunate today I'm teaching from a place where I know that it can happen, like for a few seconds the quality of the connection drops, and it's good that you let me know. Okay, so now it's better, now everything's fine. Okay. So again, so what we will be up to, that we will design a general scheme of a search algorithm, and depending how the algorithm selects the next node for exploration, this is the main thing, the algorithms will differ. Okay. Okay, I'll just make sure that okay, sound okay, good enough, variable, silence. Wait. So how's the voice now? Just to make sure that it's okay. Good enough. Okay, so if it's good enough, then fine. Okay, thank you. So a general scheme of a search algorithm. Okay, so let's try to implement a tree search where the input is a problem or environment. Okay, so this is something that, say, think about the simulator. So this is something that someone programmed to you, and you are up to finding a solution or failure. There is no solution. Okay. Okay, so we initialize by using the initial state of the problem. So this is the, like, putting the array in some, data structure, making sure. So this is the starting node. And then there will be a loop that, okay, if the list of nodes to be explored is empty, so meaning if there is no candidates for expansion, and we didn't reach a final state before, then obviously it's a failure. No solution exists. The opposite, if there is something to explore, then let's pick up a node for extension. I took the node for expansion, and if the node contains gold states, then we are done. And if not, if there is no, if it's not gold state, then expand some next node and add the new node to the tree and loop again until simply the loop ends either here or here. Okay, so this is the general scheme of a tree search algorithm. Okay, this is visualization of what is before. This is one possible way of searching a tree. So, of course, as we already discussed, the important question is which node to explore next, and I mean, what's the desired property of the algorithm? So we are looking for some strategy. So we are looking for the algorithm. Okay, so definitely a good property would be to find a solution, if it exists, of course. If a algorithm satisfies the property, do you know how is it called? I mean, it's not that much important to know how is it called, but if you would be discussing someone, and remember at least few terms. So a algorithm satisfies this property that it always finds the solution if exists.
A complete algorithm, I think.
Yes, indeed. It's a complete algorithm. So if it finds the best solution, so what is the adjective we are using in that case?
Optimal.
Optimal, indeed. And of course, as we said, there could be many strategies. They may differ in how many steps are needed to reach a solution. So it's time complexity. And of course, to proceed, we'll also need to study the space complexity or memory complexity. Simply, how much does the algorithm need to remember throughout the search? Okay. And then it comes back to the question, how many nodes are in a search tree, in fact? And what are the tree parameters? Okay. Yeah, I have the slide. So to visualize the tree, we will be using this kind of simplified triangle. Okay. So in the depth 0, there is one node. In the depth 1, there are B nodes. In depth 2, there are B2 square nodes. And the B, so meaning, for instance, here, the number of possible outcomes, the number of possible next states, this is something which is called branching factor. Okay, and for instance, for the map problem for finding the shortest path, it's the average number of connected cities of the how many cities are next to the city. It may vary throughout the problem, so that's why I would typically use the average branching factor. I hope that I remember it well. For instance, the chess. Would you guess what's the chess game? Would you guess what's the branching factor for the chess game? Type some number in the chat. Okay, she no answers. But anyway, okay. I hope that I remember well. The average branching factor for chess game is 35, and a special tree, special kind of tree. It's a binary tree where b is equal to 2. So the binary tree is indeed the smallest or thinnest tree with the least number of nodes. Okay. Then, so these violet numbers, those are the depth, and the S is denoted the shallowest depth, or the smallest depth, or shallowest goal. Okay, so there could be actually multiple goals, and we denote the depth of the shallowest one by S, and M is the maximum depth of a tree. It can go to infinity. It's worth to remember. Okay. So as we see, so we have B2, so number of nodes, it's B to M plus B M minus 1, and so on. So this one node can be seen as a B power to 0, and B nodes is B to power 1. So it's I recommend just try for some numbers, put it into the computation just to get a flavor how big the trees could be. And whenever you are studying problem, it's good to one of the possible ways is to study it from extrema. So we see that for b equal 2, it's the thinnest tree is the least number of nodes. So for instance, one can start with b equal to 2 and to study the property. So this is the thinnest possible. So anything else will be worse in terms of number of nodes, right? And you will see that indeed, as is the exponential problem, this last depth, of course, vastly dominate the number of nodes. Okay, so let's start with the first strategy: how to select the how to build the search tree. In fact, okay, it's called the depth first search. What does it mean? Okay, so we are here. We can see that from S we can go to A, C, and D. Okay. So this is the answer of calling the question, give me all the next states. Okay, so now this is the frontier. So these are the nodes to be explored. Okay. So So the depth of all those states is the same, because the depth is the number of steps. So here we have the depth 0. This is the depth 1. So then I can continue iterating, picking one at random or some other criteria, like for instance, using the alphabet to the first one. Okay, so now it's A. So from A, I can go to E and to B. And that will be probably it. Okay, now my frontier, or the list frontiers, is this one, right? So those guys were all explored. And the depth of this node, it's equal to 2, because it took 2 steps to go there. This is 1 and 1. So as I'm going first to the maximum depth, I am following this or this. And we said that we are using the alphabet for selecting the, then I'm B. And from B, I can see that I will have a chance to go to F and to E, and that will be it. So again, now the frontier is this, right? So the depth of those guys is 3, 2, 1, 1. And one of those, it's E. Here can go to F. So now this is the frontier. So this is the 4, 3, 2, and so on. So again, you can see that you have the F, the state F at the moment twice. And I see here from F, there is no way out, which, so the function give me the next state returns empty. So, but I know. So this is the definitely dead end. So this is again explored. There is no way out, so it's explored. So those guys already also explored. So what is the next deepest node in the list of frontiers? Is here this one, this guy F. So I will repeat the action. I will try to explore this, and again I will end up with the same, right? So there is no way out. So next guy deepest is the E, and so on and so on. So now the so this one explored. So this is all explored, and those are the remaining frontiers. So I'll repeat the procedure, and here I found the G. So as we remember the general scheme of the procedure, then this algorithm stops here, saying that the G is the goal. So the I can do the backtracking because each of the node remembers its ancestor. So this is the solution that the algorithm yields. Okay, so this is the strategy called depth first search. Okay, so what's the time complexity of the depth first search algorithm? If you don't know the answers, that's try to give intuitively the answers. Again, I am not grading these answers, so don't be too worried. Okay, thank you. So all good. So, indeed, the time complexity is b power to m. In worst case, it can happen that I will need to go through the all tree, right? So this is the tree. And even though the solution could be, somewhere here, yeah, it can happen that before ending here, I would really need to explore all this stuff somewhere here. Then suddenly, miraculously, I can appear here. Okay, in the worst case, it can be really B2M. So what is the space complexity? So again, that corresponds to the number of nodes I need to remember in order to yield a solution. Okay, thank you. Okay, so this is a little bit more varied, the answers. Okay, so let's try to discuss how the algorithm works a bit again. So what do I need to remember? Okay, so here in this particle, we explored one state and we remembered sort of one layer of the of the tree, one depth. Then I follow this deepest path here, and I'm always exploring here and here. So I definitely remember. So what I had to remember, this, then this, then this. Okay, so I am going deeper. So it will definitely depend on M, right? And in each of the depth, I have to remember all the successors, like so the number of successors is dictated by B. But on the other hand, the good thing is that somewhere I end up with at the dead end, like here. So this is the dead end. So I'll go here. Okay, well, that was probably not a good idea. So I will go here. So again, this is something I need to remember. But also the good thing is that this guy could be already discarded from the memory because I don't need it anymore. Okay, so at the moment I need to remember this, and this. Okay, so as I am recovering from the dead ends, I can forgot. Oh, that's again the violet. I don't know. Okay. I can start forgetting this part. Okay, and this all somewhat moving, traversing the whole tree. Okay. Okay, so I repeat the survey. To see if anyone or if someone changed his mind. Okay, it didn't change much, so apparently my explanation was not good enough. So it's linear. So the good thing, this is the good thing on the depth first algorithm. So it's B times M, right? So we need to just remember the small part of the tree like this one. Okay, we are going deeper. Here I'm simplifying the tree structure like that. The branching factor is mostly just 2. Okay, so this is what I am exploring. And here say this is the dead end. Okay, so this is the B times M. Okay, now, so we reach the very end. Okay, this is the dead end. So I'm recovering. So here, this is again the dead end. Okay, so this is something I really don't need to remember anymore. Also not this one. Okay, then I'm adding, say, here and here. And now I remember this red and violet again. And it's again just the B times M at worst. Okay, and as I'm recovering back up and up, I'm always forgetting, or I may forget all those nodes that were not successful. Okay, so this is actually the good thing on this algorithm. Okay. So completeness, yes or no? Is it complete? Okay, so I received at least few answers. So all of those who answered think it is complete. Yeah, it's a bit tricky question, but in general, it's not. And the reason is that the M actually can go to infinity. Even if the goal is at the finite depth, like the S, okay, this part can really goes to infinity. Okay, so in general, it's not complete. Of course, the depth first search can be implemented in a way that it's complete, like limiting the depth, but in general, it's not complete. Is it optimal? Once again, the optimality means that the algorithm always finds the cheapest path. So the first question is, of course, what's the cost here, right? So most of you think that it's not optimal, and indeed it's true, because the cost here is the depth of the found goal, right? And we remember that a goal could be here at the maximum depth. The goal could be somewhere here in the shallower depth, and also here. And of course, within this algorithm, as we are following the depth first principle, it easily happen that the first goal recovered would be this one. Okay, it's definitely not an optimal algorithm. So any questions so far? Okay, the breadth first strategy. So as the name suggests, we will be trying to cover all possible solutions to the certain depth, right? So this is the frontier list of nodes, and again, they do have all the same. They have the same depth at the moment. So I'm picking one according to the alphabet rule. So the A. Okay. Now the frontier is this. And the depth of those guys, it's 2, 1, and 1. And here the rule is the opposite. So instead of taking the deepest, I'm taking the shallowest node next. So in the next, I will be exploring this node, C. Okay. Here the frontier. So this is the list of frontiers. And this is the list of explored. Or closed. And now this is the shallowest one, right? So this is 1, and all those guys have 2. So I'm exploring the D, and here while I was putting the G in the list of the list of frontiers nodes, I got the message that the G is the final state, so I stop the algorithm here. And we want to study the properties of this strategy. Okay. So what's the time complexity? So again, the B is the branching factor, M is the maximum depth, can be infinite, S is the depth of the shallowest goal. Okay, so I got most of the answers. Okay. So what I need to remember, right? So we saw that we are really exploring the space thoroughly, depth by depth. And I definitely need to remember, right? Even at the end, I remember all those guys here, right? And of course, as I'm going depth, one depth by another, I stop here in the depth S. Okay, so the time complexity is B to S. So this guy. Okay. Okay, I was talking about the space complexity, but in fact it's the same as the time one here. So it's a good thing. Okay, so I already answered also the space complexity here. Okay, so about the optimality. So is it optimal? Sorry, is it complete? Mm-hmm. Yes, it is, because it always, as we saw, it stops at S, right? And if S is finite, then it always finds a solution. So is it optimal? We see that we are looking for a solution that yields the minimum depth. Okay, it is optimal, right? Because we are really going through the search tree very thoroughly, and so we always explore the whole set of nodes at the given depth before going to the next depth, right? So we never miss the optimal solution at the depth S. And actually the time, I was not entirely right because I was discussing the space, actually what to remember. In fact, the time complexity is the sum of all those guys, right? So in fact, it's 1 plus b square b3 plus. But again, if you put some b here, you'll see that this last layer vastly dominates, right? So even for the binary tree, this guy is slightly bigger just by 1 than all this sum before. Okay, so even for the thinnest tree. And of course, the branching factor is typically more than 2. So what we are always interested in is the last exponential, right? So that's for us the most important. Okay, so this is the comparison. You can go it through one by one yourself. So here it seems that for the simple problem, the breadth first search. Okay, so this is the breadth first search. This is the depth first search. It was more successful, right? The tree is smaller than the depth first search. Okay, but the memory, don't forget that the memory complexity is exponential for the breadth first search. Yeah, and just try to put some decent B and decent S, and you will see how quickly you can go out of the memory. Okay, so of course, even waiting for the result exponential, it's not particularly good, but okay, you can afford some waiting if really needed. But even with nowadays computers, the memory is somewhat limited, and some care typically has to be done in order to avoid, overflowing memory in order to get some result. So the main take-home message is that really be aware about the exponential complexity, and for many problems, the breadth first search, even though it's optimal, complete, it has all those nice properties. It may be difficult to apply this strategy, at least directly. So how to solve the dilemma? Okay. So for instance, let's think about the depth first search with the limited depth. Okay. So now the algorithm depth first search stops with the depth equal to. Okay. So now we reach the maximum depth. So this is the frontier, depth 2, depth 1, depth 1. But we reach the maximum depth, right? Here we looked next, but now the depth of those guys is already 3, so we don't follow, don't continue in this direction. So again and again. So this definitely solves our problem that the depth first search could fall in the infinite depth problem. And the question is, of course, what should be the maximum depth, right? Let's transfer it in the map problem, right? Okay, so this was the map in here, and there are some paths in between. And the maximum depth here corresponds to the maximum number of paths between any pair of cities. Okay, so because the problem can be set arbitrarily, like going from here to here, or from here to here, and the max depth should correspond to the maximum number of transitions between any pair within the map. Okay, which can be unknown, of course. Oh, I got some message. Yeah, the question is about time complexity of depth first search. Yeah, indeed. And as Kolega Malek correctly points out, so far we have a graph without loops, but in general there could be loops, like so if I add a arrow here or the path here, it creates okay, actually not. I have to put also here, then it creates a loop here. Okay, so in fact, and this a loop can create an infinite search space, right? So I can here loop forever and increasing the depth of the solutions, right? So if I have a problem that may contain loops in within, I need a little bit care how to work with the nodes. We will be discussing it. I'm not sure if today, but definitely next week. Okay. But indeed, the complexity of the depth first search depends on M, not on S, and M can be infinite, right? So in general, indeed, the depth first search can be infinite. But if implemented correctly, I can avoid the looping. But then it adds, if I want to avoid looping, then of course it adds the space complexity, because I need to remember more. Okay, then so if I'm using the depth first search and I am adding a mechanism for avoiding loops, then I need to remember more, and I'm losing the nice space complexity. The avoid nodes, that's a good question, because here the question is, could we not avoid the nodes which have been already visited? Again, that brings us back to the discussion about the difference between a node and a gate, right? what is meant here rather is that not nodes which have been already visited, but cities that have been already visited, which is quite easy because we know that every city appears in the state space just once. So, and obviously, if we are again in the same city, we are sure that we've been already here. But in the search tree, in the nodes, this guy is not the same as this one. Okay, it says that we are in the same city. Okay, but they differ in the history. So here, for instance, this D encodes the information that it took 2 steps to get in here, and this one just 1. Okay, so if we optimize the depth, then of course this guy is better, but the criterion may be different, as we will be talking probably next week. Okay, so it's not that easy to say. It's not that easy in the algorithm to avoid looping because this D and this D is different. Okay, so a good strategy could be to do the iterative deepening. Okay, we start with a small maximum depth, say 1. We perform the depth first search. I mean, the classical one with a very simple memory handling. So having the nice linear memory complexity. And of course, this can end up well, either finding solution or reporting failure. Okay, if algorithm doesn't find a solution, that simply we can clear the memory, increase the maximum depth, and repeat. And repeat and repeat. So we are essentially repeating the steps we already did, right? So in a form, it's a waiting time. So the time complexity of the iterative deepening search, right? So it suggests that it's really wasting. So we know that the standard complexity of the time complexity, the standard complexity of the depth first search is B to M, right? The M is the maximum depth of the problem. Okay, and remember that the shallowest depth of a goal is S, right? And as we are here really, you know, the first depth first search ends up here, then we increase the maximum depth and so on. So we are repeating the searches, and obviously this first we do S time before we reach some solution in the depth S. This one we do S minus 1 times, right? Because this initial search we always do the same. Okay, so it's S time B plus S minus 1 B squared plus S minus 2 B cube, and so on until we finishes at the B power to S. Okay, so it really sees that we are repeating many things, but it's good just put some numbers here, right? So if we say that the branching factor is 10 and the S, the shallowest depth is 5, say, then the iterative deepening search is, I counted it in advance, so I hope that I did it right, is 123,450. So that's the iterative deepening depth first search. And the breadth first search, because this is the one we compare with, right? Because the breadth first search does this at once, right? But it has to remember everything. So it's B2S. Well, it's not B2S, right? Exactly. It's B plus B square plus B up to B power to S. What's missing here are the multiplicators, right? So here are no multiplicators, those guys. But if you put numbers there, it ends up that's like 111,110. So, and if you compare those numbers, the difference, it's not that scary. And the good thing is that this algorithm still preserves the nice linear complexity. So at the worst case, the memory needed is B times S. So actually, the iterative deepening is the one. It's the algorithm that is very often used for real-world problems, the difficult problems. Okay, so far we've been optimizing the depth. But in general, we can optimize, for instance, for the kilometers, for the path length, or the fuel consumption, if you say. Here, the numbers correspond to the expenses. Okay, so it costs 3 units, whatever it may be, from S to D, 1.5 from A to E, and so on and so on. So we need some cost-sensitive search. Okay. So we do it explicitly. I thought that I had it one by one, and apparently not. Okay, nevertheless. Okay, welcome. So this is the same. Sorry, my fault. So in breadth first search or depth first search, we obtain the number of depths, and those are the numbers I was writing by hand into the tree. So the depth of the S of this node is 0, and the depth of this node is 1, and this is the depth 2. And we were using these numbers, the depths, to steer our search. Okay. So and now we have a numbers corresponding to cost. So how it works? So now I will be maintaining the uniform cost frontier. So before going to some more promising direction, I want to make sure that I'm not missing any shorter path. Okay, so how to do it? Problems on the connection. Okay, so it starts. Those are successes. So now the frontier is here. So I am taking the most promising candidate here. 1. There are 2 nodes with the cost 1, and again I may be being one by using the alphabet criterion, okay? So now this is the frontier. So 2, 2.5, 1, and 3. So obviously I will be taking this one. Again, now this is the frontier. And as I'm using the alphabet criterion, I will be exploring this node. Again, now I have this as a frontier. I'm following the cheapest, okay? So another important question is when to stop, okay? So previously, when we were optimizing the depth, we stopped here, okay? So let's say we can stop here, okay? And the cheapest path to G when I'm backtracking is from S to C, C to D, and D to G. So the cost it's 3. Okay, sounds okay. There's probably no cheaper path. Okay. So now I edit. So this is a slightly different graph. Compare one by one. So here I had 1. And now I have 1.2 here. And I added one path here, 0.5. Okay. And we will be following the same scheme. So expanding the first layer, taking the most promising one. Again. And now, okay, now the frontier, now, so I expanded the D. I looked to the ancestors of D, possible ancestors, and I found that there is a G, the goal state, with the cost 3. So using the old rule, I would stop here, saying that this is the cheapest thing you can do to get to the goal G. Okay, but I'm saying it's not a good idea. It's better to stop the algorithm in the moment when it's being explored. Okay, so I am continuing. So I'm saying, okay, there could be a better path to here. Okay. Sorry, I forgot one frontier. This is still a frontier. And this one too, actually. No, this does not. Okay. So I'm continuing. And the most promising is this F guy here because it has cost 2.2. And now the frontier is this list. Okay. Now the most promising is this one. So I am taking this node from the frontier list. I'm looking into it and I'm seeing that it's G. So the final go. And now I'm stopping it. So I'm taking this guy out, trying to explore. But while I'm doing it, I'm checking its content. And I see that it has G. So this is the final go. And I'm stopping it here. And now I see that this is the cheapest path, right? So from C to from S to C, C to F, and F G. Okay, so to make sure that my uniform cost algorithm always finds the shortest path to be optimal in a way, I have to postpone the stopping the algorithm to the moment when I am taking a node from the list of frontier and going for exploration. So it's important not to stop prematurely this algorithm to make sure that it's optimal. Okay, I'm finishing this today's presentation. Okay, I'll skip this here. What I definitely recommend to you, just use this graph and try to make a path through, or better say, try to create a search tree by yourself on a paper. You know, just use the uniform cost algorithm and build the tree by yourself. Okay, so it's like S saying the cost is 0, then it go to this some other nodes and so on and so on. Try it by yourself. It will help you to understand the algorithm, and it will help you with the implementation. Yeah, the complexity of the algorithm is actually very much like the breadth first search, right? Because it's the similar strategy. But there is a subtle difference, and the both time and space complexity is equal to B. So it's the basis is the branch factoring again, but the power is C over epsilon, and the C with the star, it's the is the cost of the minimal path, or the cheapest path, and the epsilon is the say smallest cheapest transition from one node to another, right? So for instance, in the classical depth optimizing algorithms, the epsilon is equal the epsilon is equal to 1, right? The minimum transition is 1 depth, and the C is S, right? So when it's like that, then this transfer to B to S, which is the complexity of the breadth first search. So you can save some time if the properties are good, but it can be also worse, right? So if your map is very, very dense, right? So if your map is very dense, you have some very small distance between the cities, then of course this can take quite a long. So what of course the algorithm typically does, there's some hierarchy in the path finding in the navigation, right? So if you are trying to find the path, say from Prague to Madrid, which is probably 2,000 kilometers as the crow flies, so there are many cities, and of course, starting from the finest level, it will take forever. I mean, this guy would take forever. Like this is the 2,000, say, and this would be, I don't know, 1/10 of kilometers or something, then of course this complexity is huge. But you can do it kind of hierarchically. Okay, so this ends today's presentation. Wait. We started at 10, right? Yeah, I make it even more longer than. Sorry. I apologize. I apologize for making it 20 minutes longer. I don't know why, but I had in mind like 11:45 as the ending time, not 11:30. So my apologies. I will yeah, we will take care about this better next time. Sorry. So any questions? So if not, then I'm finishing the recording.